Welcome back. Last time we used a pictorial derivation to obtain the equilibrium equations of force and moment for a continuum. Today we'll do a more mathematical derivation. Let's start by considering a body B and in it an arbitrary region R with surface S, and acting on the surface attractions T superscript N, and acting on the volume of the region body force vector B per unit mass. For B in equilibrium, we assume that any arbitrary region R of that body must also be in equilibrium. So that means that the sum of the forces acting, which would equal the surface forces plus the body forces, must be equal to 0. Now the surface forces acting on the region would be the double integral over the surface of the surface tractions Tn with respect to S plus the triple integral over the volume of rho times B. B is body force per unit mass, so rho times B is body force per unit volume. Writing this in index notation, we obtain the double integral over the surface S of Tj with respect to S plus the triple integral over the volume of the region R of rho times Bj with respect to volume is equal to 0. So now we can use Cauchy's formula and the divergence theorem to simplify these integral equations and turn them into differential equations. First, we use Cauchy's formula so that the surface tractions Tn become Ni Tij. So the previous equation becomes the surface integral over S of Ni Tij with respect to S plus the volume integral over R of rho times Bj with respect to V is equal to 0. To go further, we need to somehow combine a surface integral and a volume integral, and to do that we use the divergence theorem. The divergence theorem states that the volume integral of the divergence of a vector is equal to the surface integral of that vector dotted with the outward normal to the surface n. The same theorem holds for a tensor, in which case we write that the volume integral over R of the divergence of the tensor A is equal to the surface integral over S of n dot A, where n is the outward normal to the surface. Or, writing this expression in tensor index notation, we get that the volume integral of del Aij del xi, that's the divergence of A with respect to V, is equal to the surface integral of Aij Ni with respect to S. So now applying this theorem to the expression that we've obtained, we would have that the surface integral of Ni Tij is the volume integral of del Tij del xi with respect to V, and then the other term remains unchanged, rho Bj dV. Now we have two volume integrals over the same region, so we can combine the terms in a single integrand, del Tij del xi plus rho Bj with respect to V is equal to 0. At this point we use a common argument or set of reasoning in continuum mechanics. Because the region R is completely arbitrary and could be arbitrarily small, the integrand, what's inside the integral, must itself be identically 0. And therefore, we can ignore the integral and just say that the differential equation inside the integral is 0. And so we get that del Tij del xi plus rho Bj is equal to 0, or the divergence of the stress plus rho times the body force is equal to 0. So these are the equilibrium equations of a continuum. Now we can do the same thing for the equilibrium of moments taken about the origin O. So again we have a body B and within it a closed region R with surface S. surface tractions Tn acting on the surface, body forces B per unit mass acting on the volume, and an origin of our coordinate frame O. Moment equilibrium requires that the resultant couple about O of the forces acting on R is 0. Now, if x is the position vector with respect to the origin O, then the moment due to the surface forces is the surface integral of x cross t superscript n with respect to s, and the moment due to the body forces is the volume integral over r of rho times x cross b with respect to volume, and this must equal 0. Now, writing this in index notation, we introduce the permutation symbol eijk xj tk with respect to s plus the triple integral with respect to r over r of rho times eijk xj bk integrated with respect to the volume. So again, using Cauchy's formula, we can say that tk equals np times capital T pk, and substituting that in, we now have that the surface integral of eijk xj np tpk with respect to s plus the volume integral of rho eijk xj bk integrated with respect to volume is equal to 0. Again, applying the divergence theorem to the surface integral of np tpk, the first term becomes the volume integral over r of eijk times del xp times xj tpk. So this again is the divergence. And the second term is the same, rho xj bk integrated with respect to volume. And then, just as before, we argue that since the region R is arbitrary and could be arbitrarily small, that the integrand, what's inside the integral, must itself be 0, which leads us to eijk times del xp of xj times tpk plus rho times xj times bk is equal to 0. Now, if we expand this derivative here, del xp of xj times tpk, we get xj times del tpk del xp plus tpk times del xj del xp. Well, del xj del xp is either 1 or 0, so it's delta jp, which means we get xj times del tpk del xp plus tpk times delta jp, which is tjk. So this then simplifies our expression to eijk times xj multiplied by del tpk del xp plus rho bk plus tjk, this term here, is equal to 0. Now we'll notice that this part of the expression is actually the equilibrium equations. This is the divergence of the stress plus the body forces. So from the force equilibrium equations that we just derived, this left term is 0, and so we're left with eijk times tjk is equal to 0. Now if you recall the permutation symbol, it's 0 when I, j, or k are equal, 1 when I, j, k are a positive permutation of 1, 2, 3, and negative 1 when it's a positive permutation of 3, 2, 1, or a negative permutation of 1, 2, 3. If we look at this expression, we see that for every jk, there's a opposite valued kj, would mean that this expression could only be 0 if for every tjk, tkj were equal. In other words, this expression simplifies to tjk equals tkj, or t, the Cauchy stress tensor, is symmetric. So this is the other condition that we had previously obtained pictorially and we can now see that it is proven mathematically. This is the condition of moment balance for a continuum in equilibrium. Next, we'll go on to look more into kinematics and strain before deriving the rest of the governing equations.